Okay. So first, some announcement. Homework 2 is out on the website. It's due next Monday at 10 p.m. So pay attention to that. And an important announcement. I'm not going to be holding office hours today from 2 to 4. Instead, I will hold them tomorrow, just for this week from 3 to 5. And exam 2 is next Wednesday in class here. And I didn't want to lose a lecture because of the exam. So instead of discussion sections, the coming Friday, not this Friday, but the next Friday, 10:30. Did I get the date right? No. Yes, this should have been 29. Yeah. On 10:29, I'm going to teach from 2 to 4 via Zoom. Okay, so this will be one remote lecture or two. We'll have 2 remote lectures for the entire quarter. And those are going to be the weeks that we have the exams in class. Okay. So next Friday, no usual discussion sections, but there will be a lecture by me, which will continue from where we're going to leave off. Okay. Any questions about that? So if you can't attend it live, at least you can watch the video, and we'll of course be there to answer any questions you might have about it. Okay. Any questions about the exam? Are you able to access the practice exam? All right. Yeah. Oh. Sorry to scare you, but this should be an exam. It happened last week while you were sleeping. So that's my recurring nightmare. Okay. So, any other questions? All right. So let's start with the lecture. So last class we started talking about DFAs. We kind of played with them. We saw some nice examples. And one of the things that you should take away from this is not the specific examples, but our thought process and how we came up with the DFAs, right? So someone is going to give you a language. How are you going to design a DFA? As I said, just become one, right? So imagine you're playing this sort of checkered game where each state is like a tile or circle, and you're hopping across them, right? And at the end, you have to tell the answer. Okay, so keep playing this game. That will help. And if you start drawing diagrams, often you might hit upon the right answer. Okay, and we also saw some important closure properties of DFAs. One was and, one was or. And one of the reasons for studying these closure properties was that often we'd like to put pieces of computation together, right? You know, I can solve this problem. Can I use this as a module for later, for solving other problems later on? Okay, and closure properties are something like that. If I can solve F, if I can solve G, then I can also solve F and G. And today, what we're going to do is kind of expand on this topic of closure properties, and also kind of ask ourselves, why are we studying these things in such detail? And 2 reasons. One, it's actually important in for some practical problems. And it also led to one of the most important ideas in computer science, which is non-determinism, as we'll see in a little bit. Okay. So one thing, I didn't emphasize this enough last time, but you should think of DFAs as ideal for pattern recognition tasks. Okay. Again, this is not a theorem or a statement. This is just like a subjective judgment that often, like, you know, like if I tell you, okay, does this string contain the pattern 1101? One way to check for that is to actually design a DFA to do that. And after that, it's a very fast way to check for this pattern. That imagine you are writing a code for trying to check if the string, the 4-letter sequence 1101 occurs in your 1 million bit long string. How can you do that? You can design a DFA and then, you know, kind of use it. And now maybe somebody comes and says, I want to check if the pattern 1101 and 0101 occurs in the string. Okay, how do you do that? Well, I can do ANDs of DFA, so I can do that. Okay. So this is just one conceptual way of thinking about one of the purposes of DFAs, which is you can do this pattern recognition using DFAs. That's not their only purpose, but it's often one of their main uses. In the same way, so as an example, suppose we can ask for design a DFA that contains 0, 0, that accepts strings that contain 0, 0. Okay, so well, let's try and do that. How can I do this? I'll always start with the start state. This is my start state 0, and my goal is to look for somewhere in the string I have to see a sequence 0, 0. How can I do that? Any suggestions? Yeah? Perfect. Okay. So, right? So basically you're looking for 0, 0. Once I see a 0, I start looking for it. And if I see a 1, I have to restart. So I jump back. Okay. But here, if I see a 0, I stay where I am because I've already seen a 0. Oops, sorry. If I've seen a second 0, so I just go to where we are. And here, if I see a 0, I'm good. And 1 is also fine. Okay. And what should the accepting state be? 2. Okay. That was, nice. But now what if someone comes and says, design me a DFA that accepts strings that do not contain 0, 0. Okay. So now I want to filter out all strings that do not contain 0, 0. Like if the string has a 0, 0, it should be rejected. Yeah? Exactly, right? So I can move this. Okay, so let me modify it. So as suggested, we can do this by just changing the set of accepting states. Okay. So more generally, so the principle here is that when we flip the set of accepting states, we're kind of changing the outcome of the function, right? So if a function f is computable by a DFA, then not f. So not of f is another function is also computable by a DFA. Okay. So the trick that we just saw is not specific to that one DFA. Whenever I have to compute the negation of a function, given that I already have a DFA for that function, I can just change all accepting states to non-accepting states and non-accepting states to accepting states. that's going to flip the outcome of the function. Any questions about that? Okay, so proof start with DFA D is T comma S for F. Set DFA the complement is the same transitions, right? You're just changing the set of accepting states. Okay? So this is all states not in S. Okay. So recall the notation that the square brackets denotes the set 0, 1 through C minus 1. Okay. Any questions? Okay. So okay, so all of this is good, right? So what did we learn from these things? So we know that DFAs are closed under OR and not. Okay. So if F comma G are computable by DFAs, then so are F or G, F and G are not of F. Okay, all of these are also computable by DFAs. Okay. So this is very good in terms of closure properties, but there are some other operations which we'd like to perform and check if you satisfy closure under even those properties. And one of the important ones that comes up in the context of pattern recognition is what's called concatenation. Okay. So let me talk about that. So as an example, right? Suppose that I really want to identify we can design a DFA to check if 0, 0 occurs in the string. Okay, we just saw this. By the same logic, we can also design a DFA to check if 1, 1 occurs in string. Okay, so just take the same construction, maybe change all zeros to ones, you'll just get exactly what we want, right? But maybe what if someone comes and says, I want to accept all strings where I see a 0, 0, but after that I see 1, 1. Okay. Imagine you're scanning through this huge text document and you want to say, I see tax somewhere in the document followed by return somewhere in the document. Okay, that's just an example. So here I'm looking for pattern one after the other. There's this notion that, okay, I see 0, 0, and then from some point later, I need to see 1, 1. Okay, can we do such a thing? Yeah?
Accepting state of the 0, 0, 0 to the starting state.
Let's see. Yeah, that's a good solution for this case. Let me, okay, you defeated my example, so let me make it a little harder. So let's say 0, 0 followed by 0, 1. That's an excellent solution for the example that I was using. But let me change it because I want to kind of identify a more general principle where I can recognize one pattern followed by any other pattern. Okay. So here the tricky thing is that the zero could overlap. Right? So if it's C 0, 0 and then 0, 1, that should be allowed. But if I just go back, then it might not be. Okay. There could be more complicated things like that. Right? Any other questions? Yeah?
Sorry, why was it 1, 1 before?
I'm just changing the example to make it a bit more complicated. Okay? But let me make it, so let's say if f comma g, oh, actually, I think I was wrong. So, hold on. So, I think that's a very good suggestion. So let's just dig into that a little bit. Okay, so let me take the seemingly easier example of 1, 1. This is just an example to illustrate what's going to come. We're going to ask a much more complicated question, but let's start with the specific example. Suppose I want to do this. So if I do 0, 0 followed by an occurrence of 1, 1. Right? So one suggestion was maybe you take the automaton for 0, 0. Okay? And then I can take the automaton for the one that recognizes 1, 1. Right? So I need to make this 0, 0, 1, 1, 0, comma 1. Okay. So this is an DFA to check if 0, 0 is in X. And this is a DFA to check if 1, 1 is in X. Right? Okay. And the suggestion was if I want to check for one after the other, maybe what I do is just go through this and add a link like this. Right? I had to first reach the acceptance state of the first automaton and then jump to the other automaton. And then start looking for 1, 1 here. Okay, does it make sense? Okay, the question was, can I design an automaton which checks for occurrence of 0, 0 followed by an occurrence of 1, 1? Okay, so you said, okay, you check for 0, 0 and then you check for 1, 1. Right? So this is great. So that works in this specific example where somehow I'm looking for a pattern occurring first and then followed by another pattern. All right? But what if I change it a little bit and say, you know, maybe we have a DFA that checks if number of ones is divisible by 3. Right? We saw a DFA like this. Okay? And we also said we have a DFA such that that checks if 0, 0 occurs in string. Okay. Now imagine someone comes and says, for whatever crazy reason, I just want to torture you. I want to check if my string has a piece at the beginning where the number of ones is divisible by 3. Okay. But then you see a 0, 0 afterward. Okay. So how can you check that? More generally, the kind of lead up to where we are going is I want to check. So suppose I have two functions, f comma g are functions okay. Then we define the concatenation of f comma g denoted as follows. So this is a new function which is going to be 1, okay, if I can break up the input string into two pieces, where the first piece satisfies the constraint imposed by f and the second piece satisfies the constraint imposed by g. Right? So it's 1 if I can write x as x1 followed by x2, where f of x1 equals g of x2 equals 1. Okay. So like concatenation, right? When I concatenate two strings, I get a new string. And in the context of functions, what we are asking is, I have this new whole string x, can I break it up into two pieces? So the first piece satisfies some constraint as imposed by f of x1 equals 1. And the second piece satisfies the constraint g of x2 equals 1. All right? And these two things are a little bit like that. If I ask for 0, 0 and followed by 1, 1, 0, 0 is like your f, right? It's checking for 0, 0 is f, checking for 1, 1 is g. The concatenation checks for the pattern 0, 0 followed by 1, 1, right? And here, when I say, okay, number of ones is divisible by 3, again, this is just some random example I cooked up, but you can ask this for much more general things, right? Imagine you're scanning through like a program code and you'll say, okay, can I look for main followed by some print statement, right? Things like that. So I'm looking for one piece in some part of the program and another piece in the other part of the program. Okay. So this is the concatenation operation. In the context of languages, it's perhaps more natural. Okay. So if L is a language, or let's say if L1 is a language and L2 is a language, then the concatenation is all strings which can be written as basically all strings that I can obtain by taking one string from the first language and the second string from the second language. Okay. Any questions? Yeah? Then it would not be, it should not be accepted.
Oh, that's part of how we
Right, exactly. We need to see the 0, 0 first, followed by 1, 1. So there's a specific order here, right? I have to first see something that satisfies the constraint of f, followed by the constraint of g.
And it doesn't have to be like immediate.
It doesn't have to be immediate, anywhere. Yeah? That's fine, right? Because you see 0, 0. Oh, I see what you're saying. Okay. Yeah, so maybe that's a good point. So somehow I should not just be drawing a direct edge. I should be merging these two things. Okay. So let's say this. Okay. So this is where 0 would go, and this is where 1 would go. Okay, it's a good point. Thanks for catching that. Okay, any other questions? Right, so that's concatenation of two things, right? And this is very important operation in formal languages, and something you might have seen in compiler theory is called the Kleene star operation. Okay, so what is a Kleene star operation? It's kind of like, here I was concatenating two languages, right? I could maybe concatenate the same language with itself. It's not just enough for me to see one pattern of 0, 0, but have to see 0, 0 followed by again another 0, 0. I could say that. So I need to see two occurrences of 0, 0, which are disjoint from each other. Okay. Or I can say, maybe I have to see 0, 0 3 times, 0, 0 4 times, whatever you have. And Kleene star is kind of a generalization of this concatenation, where I keep on concatenating the string repeatedly. What do I mean? If it's again easier if L is a language, then L star is defined as all strings X, which can be broken up into pieces, any number of pieces, but each piece should be part of L. So earlier we were just asking for 2 pieces, but here I'm allowing you to break it up into 3 pieces, maybe 4 pieces, how many ever pieces you have, but it should be, they should all be in L. Okay. Any questions? So, for example, if I define L as the single string 0, 1, okay? This is a language defined by single string. It only has 0, 1. What is L star equal to? What strings are part of L star? So it means you really need to have 0, 1 followed by 0, 1 followed by 0, 1 followed by 0, 1. Right? So it's just repetitions of 0, 1. So for example, this would just be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so on. Okay? Let's do one more example. What if L is 0, 0 and 1, 1? What is L star? Any guesses? Yeah?
0, 0, 1, 1.
Exactly, right? So basically, somehow every bit needs to repeat itself immediately. Okay, so this would just be, let me write it in English. So all strings such that odd position bit equals next bit. Okay, so just 1 second. So anything, you know, if I look at the bit in the 5th position, it should equal the 6th bit. That's why every bit needs to kind of, you're duplicating every bit. Right, so for instance, 0, 0 would be there, 1, 1 would be there, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, and so on. Right? Yeah?
Is the key story history?
Oh, yeah. Yes, it does. So, I mean, that's, again, it's a convention. You can go it either way, but I think the standard one that people use is that it includes empty string. Okay, and if you've seen some kind of, like, you know, if you've done like grep search or something like that on Unix, you might have seen the star operation, which is really the clean star operation, right? So for instance, if I take L to be letters A through Z, what is L star? It's any sequence of strings, of letters, right? Okay, so very compact way of denoting combinations of stuff. Okay, any questions about this? Yeah?
Is F next to descriptive or
They can be the same. There's no constraint that they have to be different.
and is that
XL, like, you know, for any arbitrary number, like the L is not constrained to be anything. You could have zeros, like, you know, maybe 1 million copies or just one. Okay. Any other questions? Okay, so that's a lot of definitions, but from a pattern recognition perspective, it makes sense to ask, can I, if I have some DFA which satisfies, if I have a DFA for recognizing a language, can I build one for other ways of combining them? Yes, we are asking for such closure properties. And one of the hardest and remarkable properties of DFAs is the following. Let's say I tell you that L is a language recognizable by a DFA. And just as a reminder, you know, the notion of languages is equivalent to the notion of functions, right? But for certain concepts, it's easier to think in terms of one versus the other, right? But they're always equivalent. It's just two names for the same thing. Okay, you can talk about clean star of a function, but I think that's less intuitive than clean star of a language. Concatenation is also a little bit more intuitive when we think of language, but it's equivalent. I can define F circle F concatenate with G in the same way as I can define L1, the language, concatenated with L2. Okay, so let's say I tell you that I have two languages, both of which are recognizable or / computable by a DFA. Is L1 concatenated with L2 recognizable by a DFA? Yeah?
What do you mean by recognizable here?
So recognizable is basically like computability. Okay, so let me write that. We say L is recognizable by DFA D if for all X, X is in the language if and only if D of X equals 1. Okay, so a language is equivalent to a function in the sense that every language defines a function where for things in the set you say 1, things outside the set you say 0. You say the language is recognizable if the same thing can be done by the DFA. Okay, so in some sense the language of all strings which contain the string which have 0, 0 occurring is recognizable by a DFA. Okay, and this kind of nomenclature comes from literally saying that okay, I pass the string through the DFA and it will tell me whether that particular property held for the string. Okay, so the language of functions and languages, they're kind of confusing, but they're really the same. All right, so that's the question now. Is L1 concatenated with L2 also computable or recognizable by a DFA? Okay, so you can go back to the function world and say, what if I have two functions, f and g, they are computable by a DFA? Is a concatenation computable by a DFA? How about, is L1 star recognizable by a DFA? Can I recognize if something is an L star using a DFA? So we're going to answer that, but it's not, it requires some work, actually quite a bit of work. So the straight, to spoil the punchline, the answer is yes. Okay, whenever something is computable by a DFA or recognizable by a DFA, concatenations of those things are also computable. Okay. And much more surprisingly, the same holds even for the Kleene star operation. Because Kleene star doesn't even look like that's something you can do with any efficient algorithm even, right? At first look. Like someone had to check all possible ways of splitting the string into pieces and then check if each one is satisfying some constraint. Right? So it seems like a crazy complicated thing, but as it turns out, everything can be done by DFS. Okay? So maybe let's just try and get a sense of what's so remarkable about this statement, right? If I'm not working with DFAs, but if I'm just working with any programming language, let's say, then I can write some simple code to check if X is in the concatenation of L1 and L2. Right? Suppose I have a DFA D1 for L1, DFA D2 for L2. Okay, and now X is my input. I want to check if X is in their concatenation. Okay, yeah?
Can you explain what the concatenation of the two languages looks like?
Yeah, so basically, concatenation of two languages is like I take a string from here, take a string from here, and put them together.
Like
All the possible combinations. So thinking about it backwards, if I give you an input string X, it belongs to the concatenation. If I can break it up somewhere, I can cut it up into two pieces, no matter the length. But the first piece should be from the first language. The second piece should be from the second language. Okay. So this is X. I break it up into X1, X2, and this should be in L1, this should be in L2. Okay. Yeah.
We do Kleene star. We have to check like all possible lengths of like x1 and x2 to see if the concatenation works out.
Yeah. Yeah, like it's not even just two pieces, right? I might require many pieces. So it's still tricky. I mean, there is a way to do it, as we'll see, but it seems complicated. Okay. But let's, imagine we're not restricted to DFAs at this point, and if I were to write a for loop or something like that, how would I check if something is in the concatenation of, if X is a concatenation of two strings, where the first piece is from L1, the second piece is from L2. How can I do that? Any sessions? Yeah?
If it's recognizable by the concatenation of the DFAs.
Yes, but well, I was actually looking for something much simpler, which is I can just run a for loop, right? If I'm not doing DFA, but you can imagine I'm actually programming this stuff up. I'll say for I in this range, basically try out all possible splitting points. Okay, that's kind of like the somewhat of a brute force approach. Right, I check if oops, this should be written one. Okay, so in some sense, what I can do is really try all possible ways of splitting. Okay. Any questions about this? This is a simple for loop, but is this a DFA? Can I make it into a DFA as written? No, right? Why? How many passes is this algorithm making over the input? Length of X, right? For basically you're saying, okay, I'm going to first check if I cut it at the middle, or if I cut it at the 10th position, if that worked. But by that time, I passed through the string, and then I have to come back and restart and say, if I cut it at the 11th position, will that work? Right? So the problem, of course, is that this is not a single pass algorithm. Okay? So somehow in your mind, we have to guess when to switch and start running the second program. Right? So we had two DFAs. We want to say, okay, you accepted the first DFA and then somehow jump to the second DFA. Right? That's what we want to do, but we have to be careful on when to jump. Any questions about what we're trying to do? And if you're talking about Kleene star, somehow it's even trickier, right? I can't even do a for loop, but you have to do some kind of recursive code to do it, but you can do it if you want to. Okay. So what we're going to do next, once we come back from the break, let's take a 5-minute break, is to solve these two things, but it involves a lot of thought. And one big idea, as I said. Okay, let's take a 5-minute break, and then we come back. We'll show that DFAs are pretty strong in terms of computing Kleene star operation. All right. So if I try to design a DFA for concatenation, you can actually, it's very tempting to try to kind of fix, maybe I can put the two things together, like, as we did in this example. We said, okay, once you reach the starting like an accepting state in the first DFA, you jump to the starting state of the second DFA, right? But that doesn't work always. You can construct examples where that would fail, even by some small changes to the one that we just saw. Okay, so you can try all these tricks, but none of them will actually work, and you have to do plenty more stuff to get it done. Okay, I encourage you to play with a few examples to kind of convince yourself why it is non-trivial to get a DFA for concatenation. Okay. Again, what if I just draw arrows from the accepting states of the first one to the accepting states to the start state of the second one? That doesn't work. So, try some of those examples. Okay, but what we're going to do today is we are going to take a different route to construct this concatenation thing. And the way we're going to do that is by generalizing the concept of DFAs substantially. And we're going to talk about one of my favorite topics in computer science, which is non-determinism. Okay. So these are called or abbreviated often as NFA, non-deterministic finite automata. So when we talked about finite automata, we said deterministic finite automata, right? They were deterministic in the sense that given a state, given where I am, and you tell me what bit I'm reading, I can tell you exactly what you're going to do. There's sort of only one path that the computation will take through, right? I see x1, I do something. I see x2, I do something. It's very deterministic. There's only one path for the entire computation once you tell me what the input string is. In non-determinism, that's not true. And this concept was actually introduced in this great paper in 1959 by Dan Scott and Michael Rabin, who, the paper was titled Finite Automata and Their Decision Problems. And they introduced this concept of non-determinism. And for this paper, which introduced this concept of NFAs, they won the Turing Award many years later. And the Turing Award, as you must have heard already, is the equivalent of the Nobel Prize for computer science, right? So this is an important concept that we're going to look at. So what are NFAs and what do they look like? Well, instead of defining them, which is actually a lot of words, let me walk you through an example. Okay. I'll first draw a diagram, and then you can tell me what's kind of wrong about it or what's odd about it. It's going to look almost like a DFA. So I'm just going to have 4 states here. Okay, so let me draw the arrows. This is 0, this is 1. Okay, but now here comes the twist. So far it almost looks like a DFA, right? I have these transitions from the CO state, from the start state. If I see a 0, I stay where I am. If I see a 1, I go to the next state. Okay, but in DFA, one of the main constraints that we had in DFA was that from each node, from each state, there are exactly 2 outgoing edges. One with the label 0, which tells me what to do when I see 0, and one with the label 1, which tells me what to do when I see 1. The main difference between DFA and NFA is that we drop this constraint. Okay, so I can have multiple edges with the same label. Okay, or I might not even have some edges at all. Like for instance, here, there is no one edge labeled 1, there is no edge labeled 0. Okay? I mean, these are like dead edges in some sense. After reaching there, whenever you see a 0, the kind of computation doesn't go through. That's not so mind-bending, but this repeating edge is a radical change. And there's one more twist, which is there are some special edges which are called epsilon edges. Okay, so I'll tell you what each of these pieces do, right? So this is what an NFA is going to look like. It's almost like a DFA, but there can be multiple edges with the same label, and some edges could be missing, and there could be edges which are the special label of epsilon. So epsilon is kind of thought of as the empty string. So NFA can have multiple edges labeled 1 out of a state. Some edges can be missing, right? And finally, some edges labeled epsilon, right? So the intuition is that whenever you have these multiple edges, you should think of the computation as kind of splitting into two parallel worlds, right? So you are here today, I give you the exam, usually there's a deterministic outcome, right? You get a score, you do well and you get 70 or 24 or 25, something like that, right? But maybe it's this, you split into two worlds, where in one universe you got a score of 20, in the other universe you got a score of 26. Right? So it's something like that. So these two branches, right? When I see a bit 1, there are two edges I can take out. One is going from 0 to 1, and the other is just taking here. So the universe is going to split into two parallel worlds. So let me walk through this example. So computation on an NFA. So unlike the case of DFS, I'm going to do the example first and then do the formal definition. All right. So let's say I want to compute what this is going to do on some string, maybe 0, 1. Zero, 1, 0, 1. Okay. So let me call this NFA N1 for the first non-deterministic finite automata we are seeing, and maybe this is my example string 0, 1, 0, 1. Okay, so let me walk through what happens. So I start at the 0 state. Let me copy it somewhere. Okay, so this is N1, and I'm trying to check what happens when you see the string 0, 1, 0, 1. So I'm starting with the start state, which is 0, and then I see the input bit 0. Okay, so what does the diagram do? When I see 0, I should just stay where I am. So what's the next state? The state I am in is still 0. Okay, so nothing radical happened. But now, let's say the next bit is 1. So there are two edges. One says, you stay where you are, the state change says where you are, and the other says go to 1. We have two options. you explore both in parallel. So the universe has split into two parallel worlds. In one, you are still at 0. In one, you are at 1. Okay? And not just that, the next twist is this epsilon. Okay? So epsilon means that you get to make that jump for free. Wherever I am, I can make that jump without reading any bit. It's like making a jump on an empty string. Epsilon is meant to signify empty string. Okay? So not only in this branch of the universe, I'd reach 1, but there is also a branch where I go to 2. Okay? Because I do the epsilon jump. And if 2 itself had an epsilon gem, I would take that 2, right? So I keep tracing out all the epsilon gems possible and create parallel worlds for every one of them. Okay? And all of this happened when I read a single bit 1. Okay? So I read a single bit 1, but my universe branched out into 3 different parallel worlds. Okay? And then I read the bit 0. So I'm now reading 0. What happens when I read 0? When I'm at 0, nothing happens. I just stay where I am. At 1, it's deterministic. So I go to 2. But for this extra branch 2, there is no edge labeled 0 out of it. Okay? So that's like a dead end. Meaning, if there is no edge labeled 0, that branch of the universe has been chopped off. Okay, has been obliterated from existence. All right? Almost like a science fiction movie. Okay, so this is like a dead branch now. And if I see a 1 next, well, I branch again. So when I see a 1 at 0, the same stuff happens, right? I can either go to 0 or I can go to 1. And then once I reach 1, I also get 2 for free. Right? And then from 2, if I see a 1, I just go to 3. Okay. So let me make 3 the accepting state, just as an example. Okay? So this is how the computation unfolded, right? So in the deterministic finite automata case, we were just keeping track of a single state. You know, I see a bit, I hop. But now when I see multiple edges, I explore all of them in parallel. When I see an epsilon edge, I just create a copy of the universe where I'm automatically in that state, right? So I keep branching off. Maybe at the end of the day, when I read the input, there are many possible options for the state of the universe, right? You know, there are many different worlds here. But I have to still tell you, when do you accept or reject? I could have been in the state 0, I could have been in the state 1, 2, or 3 after reading the string 0, 1, 0, 1. When should I accept? We have to make up some rule for that. Any suggestions for maybe when to accept? Like in the DFA case, we said if you end up, the final state you are in is an except state, you output 1, otherwise you output 0. The final state you were in was in the set S, you're outputting 1, otherwise 0. But here, there's no single state that you could be in. Right? There are different branches. Okay, so what can you do then? We have to come up with some convention, and basically the convention that's used is you output 1 if on any branch you end up in an accepting state. Right? So imagine all the choices the machine is making, each one leads the entire thing to a different path, and if on any one of these sequence of choices, right? Choices meaning for each one there was like 2 different edges that you could take, right? If on any one of those branches you are ending up in an accept state, you say the answer is 1. Okay, so any questions about this? Yeah?
Is there a notion of like short circuiting where once we find one, we just like stop doing the entire computation?
Not really, right? Because the acceptance is still defined only when you read the entire input. Okay, so like for instance, if in the middle somewhere you saw the state 3, you cannot accept. If you see the state 3 in the last sort of layer here, okay, kind of the depth determines how many bits you've seen, and the space that you're seeing on a single line are like what are the possible worlds you are in after reading so many bits. The decision of accepting has to be in the last layer. And you were right in some sense that maybe if this branch itself accepted, I can sort of already say accept. But this is not at all like any computation model, like in any computer you think doesn't like do parallel exposition, right? We're all deterministic creatures, more or less. Okay, so this is really like a thought experiment, right? For the time being, at least. Okay. So let me draw like maybe a more elaborate picture. So how does a computation go? You start with the start state, and each time you read a bit, there could be, it's not necessary, but there could be many edges with the same bit. Maybe this is x0. You read the first bit, maybe you're branching off into 3 different states. Maybe this is 5, 7, 11. Okay? And you read the next bit, you could be branching off again here. Maybe here it's only 1 branch. And maybe this is a dead end. A dead end means that branch is being cut off. Okay? And you can also get this lateral epsilon transitions. Right? So now maybe you take a step because of x1, but then there's an epsilon edge that also shows up here. All right? And you keep going like this. So explore all edges in parallel. If you're looking for a one-line summary of what NFAs are in relation to DFAs, it is this. Basically, you explore all edges in parallel. In contrast, if you think of this is how NFAs look like. DFAs would just be a straight path. Like, I start from 0, I see a bit, I go to some other state, and then some other state, and so on. Okay? And when you reach the end of the input, there are some strings here, right? Some states, and if any of these is an accept state, you accept. Okay. All right. So that's, that's two, sort of informal definition. Let's now define it formally. Once we have this picture in mind that you're always branching off, you can define it formally. Okay. So here's the formal definition. It's a bit of a mouthful. So formal definition of a NFA. Okay. So the first thing I need is, so there's this notion of power set, right? So if I have a set C, which is 0, 1 through C minus 1, you have this brackets. The power set of the set is all possible subsets. And it is a set of subsets. You might have seen this in your discrete math class. Power set is the subset, is the set of subsets. Look at all possible sets that are contained in my sequence 0, 1 to C minus 1, and those are all in this set power C. So why are we talking about power C? Well, the transition function in an NFA is a lot more complicated, right? So earlier for a DFA, we had like transition function and the set of accepting states, right? It's the same here, but the transition function is going to be a lot more complicated. In what sense? So for DFAs, the transition function took a state as input and a bit as kind of the label for the edge. And then we gave out another state that you're going to end up at. So what should I output for NFA? I'm at a state 0, I see a bit 1. What should the transition function tell me? There can be multiple edges out, right? And there's no specific order in which you have to explore those parallel worlds. It tells me a set of possibilities that you might end up in. Okay. Given where I am and a bit, I'll tell you, okay, after doing this step, you might be in either 1, 3, 5. I mean, any one of 1, 3, 5, 7. Okay. So going back to this diagram, so when I see, maybe this diagram here is clear. When I'm in this state and I see the bit 1, I could be in 0 or I could be in 1, right? But NFA could put one edge from anyone to anyone as well here. So there'll be multiple edges. So the way to capture that mathematically is to say, I'm outputting a set for each transition. Set of options, each one is going to be explored in parallel. And S is still a set of accepting states. Okay. And on an input X, N of X is 1 if on any branch the final state is in S and 0 otherwise. Okay? Make sense? So on any branch you end up in the set S, you output 1, otherwise you output 0. This is almost complete, except I haven't told you what to do on this empty this epsilon transition, right? So some of the edges could also be labeled with this epsilon step. So I can see a 0, a 1, or an epsilon, and every one of them, there could be multiple edges out. Okay? Any questions about this? If not, let's do one example just to translate this formal, to connect this formal definition to a diagram, and then we will see why NFAs are so useful. So let's say this is epsilon, this is the start state, this is 1, this is 0, this is 0, 1. And maybe this is the start state. Okay. So here's an NFA. It is an NFA and not a DFA because, well, two reasons, right? One is you have this epsilon transition, which is not allowed. And also because you can see that 2 has 2 edges labeled 0. When I say 0 out of the state 2, there are 2 branches. You know, I can stay where I am or I can jump to 1. So this is equivalent to, if I want to draw a transition diagram, so let's say this is state 0, state 1, state 2, input bit 0, input bit 1, input bit epsilon. Okay, so when I see input bit, when I am in state 0 and I see input bit 0, what is the NFA doing? Well, there is no edge labeled 0 out of it, right? That's like a dead end. You're cutting off the branch there. The way you write it is you make it be the empty set. So when I say that the transition is outputting the empty set, that just means that there's no edge with that label. And if I'm at state 0 and I see the edge 1, where do I go? State 0, edge 1. There's only one edge, so it's the state 2, right? So I end up with the state 2. If I see epsilon, then I'm here. Okay, so this is 1. And if I'm in state 1 and I see 0, I still have only one option. So I go back to 0. And if I'm in state 1 and I see bit 1, there are no outgoing edges labeled 1 out of this, right? So mathematically, that means that the transition function is saying, okay, you're going to the empty set. You're cutting off this branch. And t of 1 comma epsilon is also phi. Okay. So this is t of 1 comma 0, t of 1 comma 1, t of 1 comma epsilon. Okay. So let me write down the final values directly. So this is going to be if I'm at 2 and I see 0, I have 2 options, right? So I have to write down the set. So this is t of 2 comma 0, t of 2 comma 1, and this is empty. Okay. So if I were to write it down mathematically, this is how the transition function would look like. But most often we will just draw a diagram like this, right? A picture is 1,000 words, and it's very much easier to picture what's happening in the picture. Any questions about the definition of NFA? Yeah?
I'm a little bit confused on what epsilon means. So if we just had two states and they were both connected to each other with an epsilon, would that just branch forever?
Well, yeah. Right, but there's no purpose in branching forever, right? So in some sense, like in one side branch, I know that these two states are something that I could reach. I don't have to create copies of them again at a level. Okay, but that's an excellent question, and we'll come to something like that later on. Okay, yeah. So what these values in the table are? So basically, the transition function, when I had to write it down mathematically, for each state and each bit, I have to tell you what's the set I'm going to end up in. What are the options that I have? Right? So for instance, this cell is meant to be P of 1, comma 1. If I'm in state 1 and I see the bit 1, what is the output of the transition function? Right? So the transition function is this function which I'm picturing as a table. And I can write down C rows and 3 columns, 0, 1, epsilon. And for each like corresponding thing, I can tell you what's the set that you're going to end up in. Okay? Yeah, I don't like the table interpretation much. The diagram is much cleaner always. Right? Any other questions? It's kind of a subtle definition, so please ask away. All right, so we spent a lot of time doing this NFA business. What is it really good for? Yeah?
On the definition said that we use 0, 1 for the second input. So does that mean we have to?
Yeah, epsilon also has to be specified at every time. Yeah. Like every state can have an epsilon edge. Right? Whenever it's not there, that means that you're cutting off that branch, like you're specifying that transition function is the empty set. Okay? All right, so what are NFAs good for? Why did these two people win the Nobel Prize in Computer Science by defining them? Well, they're really, really magical. And what's the magic behind them? They let you do all kinds of things very easily. One of the hardest things, for instance, is to guess when to make certain choice. Okay, so let's see an example. For, let's say L1 is a language recognized by a DFA, D1. L2 is a language recognized by a DFA, D2. Okay, so maybe imagine this is my D1. You have 0, you have zeros and ones. Maybe this goes to state 1. State 2, maybe 0 takes you to state 10, state 17, so on. Okay, and maybe some things are accept states, right? Maybe this guy are the accept states. Okay, this is just D1. And let me also draw D2. And maybe this has some accept states. Okay. So my claim is that whenever I have DFA for a language L1 and a DFA for language L2, I can easily get a NFA for their concatenation. So the question we started out was like, can I get a DFA for the concatenation? That seemed hard because we had to guess when to switch from the first DFA to the second DFA. At some point, I had to stop following the transition instructions of the first machine and switch to the second machine. But we didn't know when to run, when to do the switch until we started seeing the computation. But at that point, maybe it's too late. Okay? But with an NFA, I want to say that it's easy. So NFA for L1, L2. Can you tell me how I can do that? Yeah?
At every state in D1, you have an epsilon branch to the starting state of D2.
From every state?
Sure.
Well, if I do it from every state, then it's not, I might jump from D1 to D2 without even accepting in D1.
Right.
Right? Yeah?
Are we supposed to combine them? You might have them both running parallel, and then we add whether they end up in a state.
That would work for the AND, but somehow when you define concatenation, you really have to break up the input into two pieces. That they don't see the same bit. I have to switch from one to the other completely, right? So I think if I just do the AND, it might not work. Very suggested. So I think it's we need to do a fix of both of your ideas. Yeah.
You can add epsilon edge for like a success state.
Yeah. Right. So kind of following from the same idea, I'm going to add epsilon edges from every accept state in the first machine to the start state of the second machine. Okay, I'm just adding these edges and nothing else. Okay, so let me write that in words. Add epsilon edges from accepting states of first machine to start node of second machine. Okay, so these are the only edges, only new edges I'm adding. Okay, and you can see that this basically works for concatenation because at some point in my computation in L1, I had to jump from the accept state to start running the second machine, and this epsilon transition edges allow me to do that in parallel for every possible jump. Okay, but once I do the jump, I'm not like going to come back to D1. Once I do the jump, it's still just deterministic from then on. The epsilon edges just allow me to kind of explore all possible positions for making the jump in parallel. All right, so that's the magic. So claim N accepts L1, L2. So let me say this is N. Any questions about this? Yeah.
Couldn't we have an accept state in D1 that would later go back to a fail state? And then that would cause like a erroneous behavior because we might get an accept state in the second.
No, but that's fine, right? Like basically we broke up the string into the piece where D1 went to accept, and then you switched, and then you started running the second machine. In the definition of concatenation, you can break up it at any point. So maybe after reading the first 10 bits, I accepted in D1, but if I read extra bits, I might not accept, right? So that was the challenge in designing the thing for concatenation, that you didn't know when to split. Right? There could be many positions where D1, within D1 you're going to accept state, but if I split up early, then I might not accept in D2. Okay, so this allows us to kind of explore all possibilities. Okay, so NFAs, you should really think of them as like, a compact way of doing brute force computation. I'm exploring all possible jumps in some concise parallel way. Okay, all right, so to me, one of the best illustration of the power of non-determinism is the Kleene star operation. Okay, so recall, if I had a language L, L star was all strings that could be broken up such that each piece was part of the language and it includes empty string. Okay, and here's my claim. If L is recognizable by a DFA, then L star is recognizable by a NFA. Okay. Once again, like, you'll see that there's some simple way to do it. What do I mean by simple way? So let's think about this. Let's say this is once again what my okay, so this is what my DFA for L look like. Okay, so let's say this is D. Now Kleene star means I need to break up my string into multiple pieces. And maybe if I read the entire thing, it's in the language, that's good. If I break it up into 10 pieces and each one is in the language, that's also good. Okay. So how can I design an NFA for Kleene star? Any suggestions? Yeah?
For any separate thing, just have epsilon and like this vector starting node.
All right, so let's try that. It's kind of like concatenation, right? Which makes sense. Kleene star is like concatenating with the same language again and again and again. So that's an excellent suggestion, which is to add these epsilon edges. Okay, so suggestion 1, add epsilon transitions or edges from every accept state back to start. Okay, and this works. All right, that's all we had to do Kleene star. Because whenever, let's suppose that I'm breaking up it into x1, x2, xl. Why would NFA accept it? I'll do X1. I'll follow the computation of the DFA until I reach X1. I'm in an accept state, and I jump to the start by the epsilon transition, and I'll start the computation on X2. I'll reach an accept state, I jump to the start, and I can jump anytime, right? I don't need to know the lengths of these things a priori. I'm always branching off. Okay? Any questions? Yeah? Right. So, 0 could or need not be the accept state. That wouldn't change anything. But you're right that there is one kink in this argument, okay? Which is that you might never accept the empty string. Right? So Kleene star by definition had to accept the empty string, which this machine might not. Okay? Because if 0 was not an accepting state in D to begin with, you are never going to accept the empty string in this new machine. All right? So that's an excellent point. I was waiting for someone to catch that. So catch empty string might not be accepted. By n. Okay? I mean, this is a problem, but it can be fixed, right? So we have to make sure that the empty string can also be accepted. And any suggestions on how I might do that? Yeah.
We just make state 0 as
Exactly. So, well, almost. So if I make state 0 as another accept state, that's fine, but maybe it might change my computation, right? Like there was, let's say, 0 and a 1 edge going back, then it would change which strings could be accepted. Okay? But we can do a small twist to what you suggested, which is the following. I'm just going to add a new dummy accept state which has an epsilon transition to the old accept state. Okay, so this is a new start. Okay, so this is just I mean, it's kind of annoying. I don't know why people define Kleene star to contain the empty string. They had a very good reason to do that, but it's kind of sort of clouds this beautiful picture that we could draw. But since that's the definition, we have to respect that. Okay. So what I did here is to add a new dummy state at the beginning, which I declared as accept, and then I'm jumping to the old computation. This is just a way to add a single empty string to the old thing that we had. But the crux of the construction is this picture here, where by adding an epsilon transition from every accepting state to the start state, we're kind of repeating the same computation again and again. So this is a little bit like recursion for free. Okay? Any questions about this? Yeah?
Can you connect the accepting state back to the dummy state instead of to state 0?
Yeah, actually that would also work. That would also work, yeah. Because somehow if I had two epsilons, it's the same, right? If I had an epsilon h followed by an epsilon h, I would trace both in the same way anyway. Okay, but that will also work. Any other questions? You had a question? Okay. Yeah?
So I feel a bit
epsilon edges. So once you get to like 17, it will automatically move back to the starting state.
It's not automatic. Basically, there's one branch where you move back to the starting state, and there's another branch where you're persisting with the old computation.
Oh,
So epsilon always means that it's like a choice. Every time you see an epsilon edge, you keep the copy as is, but there's a parallel world where you take that step. So there's one world where you don't take the step, and there's one world where you take that step. But that's an excellent point. I should stress that. Whenever you reach a state and there's an epsilon transition, there's one branch where you're continuing with the old computation. There's another branch where you take that step. Okay? So that's the power of NFS. But just adding these few edges, we could recognize clean star operation, which seemed very tricky, right? If I had to do a single pass memory algorithm, how can I do that? All right. So next class, when we come back, we'll see why we're looking at NFS, how much more powerful they are than DFS. They seem really magical beings, and they are in some sense, but we will understand the power better.